In this video, we're going to do a few extra examples using the properties of logarithms. So let's quickly remind ourselves of the property. So one of the most important ones is the definition property, which I've written up here. So if y is log base a of x, that means that a to the y is equal to x. So the base of the log is the base of the exponential, and then the other thing is swap sides, is how you can move in between the logs and the exponentials. Now, if you want log base a of 1 for any a, that's always 0. Okay, so it's what power do you need to raise a to get 1, which is always 0. If you have log base a of a itself, this is going to be 1. Log base a of a to the x is going to be x. Now notice here this is very similar to this one, and this would be exponent 1, so it actually is this rule. It's a more specific version of that rule. The logs and the exponentials are inverse functions, so if you do the log of an exponential with the same base, they should cancel out, and that's why we just get x. Similarly, if you do an exponential of a log with the same base, again, cancel out, you just get the inside here, which is x. If you have log of any base, so base a of a product, so m times n, you can split it up into two logs by adding the two. So log base a of m plus log base a of n. Similarly with division inside, you can split it up using subtraction. So log base a of m over n is log base a of m, the top, minus log base a of n, the bottom. If you have log base a of m to a power r, you can bring the power down. So this would simplify to be r times log base a of m. Also, since log is a one-to-one function, if you have log base a of m equals log base a of n, that actually means the inside bits have to be equal. Now you want to be careful if you have log base a of m plus or minus n, so if you have a plus or minus in between your two things, you cannot split it up. So however you might think you can split it up, it's not going to work, okay? You want to leave it like that, it's stuck like that. So let's do some examples. So part B here, I have 2 to the log base 2 of negative 3. So you might think that this should be negative 3 because that's what the rule says it should be. Although this one does not exist since log base 2 of negative 3 does not actually exist. Okay, so the domain of log base 2 of x is x bigger than 0, so 0 to infinity, which it means that negative 3 is not in the domain. Okay, so we cannot evaluate log base 2 of negative 3. So because the exponent doesn't exist, the whole thing doesn't exist. Okay, part C, we have ln of e to the 4. So here we want to remember that ln is actually log base e of e to the 4. So because the bases are the same, this is just the exponent, number 4. Log of 1, log with no base is actually log base 10, but it doesn't matter because we're taking it of 1, so it has to be 0. So log, no matter the base of 1, is always 0. Okay, you can also put logs together and split them up, so we're going to do an example of each. So the first one, here we have log base 2 of the square root of x squared plus 1 over x cubed times x plus 1 to the 4. So we want to split this up into a bunch of different logs. Okay, so the first thing I'm going to do is I see that I have division here, so I can write that using subtraction. So it's log base 2 of the top, so square root of x squared plus 1, minus log base 2 of the bottom. So that's x cubed times x plus 1 to the power 4. Okay, now in the second log over here, I see that I have multiplication. So I can also break that up. And I'm also going to just rewrite this inside here so that using the exponent. So a square root is like a power 1/2. So this first part is going to be x squared plus 1 to the power 1/2. Okay, now here I need to split the second one up with addition. Okay, but so I need brackets because this minus goes to this log. Okay, so that means if I split it up, it should go to actually both things that I split it up into. So I'm going to use these extra brackets. So this is log base 2 of x cubed plus log base 2 of x plus 1 to the power 4. Okay, so now I can use, finally, I can bring all these exponents down to the front. Okay, because they, that's the rule. But I also am going to put this negative through to get my final answer here. So it is 1/2 log base 2 of x squared plus 1 minus 3 log base 2 of x minus 4 log base 2 of x plus 1. Okay, now these logs with the pluses in them, I can't break them down any further because I cannot split when I have plus inside. Okay, so they're stuck like that. So this is the most simplified I can make it. So that's how I'd want to leave my answer. Okay, now going the other way, so here I want to write it as a single simplified log. So I'm first going to bring the power up. So this is ln of 8 to the 2/3 minus ln of 3 to the 4 minus 8. So 8 to the 2/3, we can simplify that. Okay, so this is the cube root of 8 squared. The cube root of 8 is 2, so that's 2 squared, so this is actually 4. And then 3 to the 4 is 81. So 3 to the 4 minus 8 is 73. Okay, so this actually simplifies to ln of 4 minus ln of 73. Okay, which now because I have a minus, I can write it as division. So this is actually ln of 4 divided by 73. So that's going to be my simplified version. Okay, now we also had this change of base formula. So we don't use this so much, but if we actually want to compute a log, and we're in a base that's not e or 10, then our calculator does not have the ability to do it. So we can switch to base 10 or base e by using this change of base formula. So if you're in base a and you want log base a of m, but you want to be in base b, you can take log base b of m, but you have to divide by log base b of base a, your old base. Okay, so if I want to do log base 5 of 18, so my calculator can't do that. So I would switch to base e, so that's going to be ln of 18 divided by ln of 5. And now I can compute that on my calculator and I would get approximately 1.796. Okay, if you prefer base 10, you could also go to base 10, so it would be log of 18 over log of 5. Same idea, you'll get the same simplification. So that's using some of the properties for logarithms to do a variety of things.